Good evening, everyone. So regarding the quiz, I will post the solutions by tomorrow, and also I will open the quiz for your review. Okay, so that I will do tomorrow, by tomorrow. Okay, so I could not do because of the busy schedule. So, but by tomorrow I will definitely do. Okay, so okay, so from the last, as I told you in the last lecture, last class, that today I will be taking the this class as a regular lecture. Okay, so today or tomorrow also, and then on Friday we will do the tutorial. Okay, tutorial for chapter 4. Okay, so we want to finish few things before chapter 4 examples can be solved. So okay, so so far the story has been that you typically have how you start. You have a differential equation, and differential equation could be of various forms. Okay, and for example, it will be something like this. You can have C1, yeah, d over dx, e, not e, but let us say either it can, okay, so not even we write like this in general. Since I'm doing this is just one example. This is not a general form. This is one example. C1 d square u over dx square plus, not plus, but it has the double derivative. It can also have a single derivative. Let us say this is C2. I'm writing minus here because it has some meaning. Yeah, so minus C2, then du over dx term can be there. Minus C3, then u term can be there, right? Plus C4. Yeah. All these also can be a function of x, right? It can be a function of x here. Okay, it's possible, right? Okay, so all these I will write all these C1, C2, C3, C4 are function of x in general. Yeah. So this is equal to 0. This is not a general form. This is one example. This is a differential equation you are given. Yeah. And this kind of differential equation we need to solve it using the finite element method. And for that, what do you do? As always, first we start with the derivation of the weak form, and then you have C1 d square u dx square minus C2 du over dx minus C3 u plus C4, right? Dx 0 to L, where x is the domain, right? So x is it defines the domain on which this is valid, right? So this is equal to 0, and accordingly when you work out you will get uh, some condition here. Yeah, so it will be I'm in this case C1, if you take it as uh, like you have to find out how it works accordingly. So finally what you get will be WC, right? WC1 du over dx, and L to 0 minus 0 to L, and then what would you find? You find du over dx, then d WC1 over dx, right? Dx, yeah, and then you will have minus 0 to L, C2W du over dx minus C3 uh, let me write W first. So W C3 U dx 0 to L plus 0 to L W C4 dx equal to 0. Yeah. So this will find out. Yeah, here also depending on what the C1 is. Yeah, so we will get two types. Either we will have this multiplied by W multiplied by dc1 over dx, right? Then in the next, if you expand this one, the next one will have du over dx multiplied by c1 dw over dx, right? So it will have dw and du and dw both. In one case, it will have just du over du over dx and w here, right? So you will get a combination, right? So you will get the terms which will have from u side and from w side, right? So you will have somewhere it will be du over dx. In that, it may be multiplied by dw over dx. Term may have this one and also may have w itself, yeah, or maybe some or also either this and this, or you will have a constant term. So you will have du w. So with you will have multiplied by w and so on, right? So what I mean to say is, looking at it, you can actually see how the stiffness matrix will be. And a stiffness matrix comes from k terms will be, in this case, you can tell looking at it, this does not have u, so this will form the force vector. Here you have u and w both, yeah. Of course, when you expand it, it will have two types, but in both the case you will have u and w both. So this will be forming the stiffness matrix. Here also w and du. So here w is there, but here your differential here there. But still, this will be taking part in the stiffness matrix, right? Here also you have w and u, so it will go to stiffness matrix. Here there is no u, just w, so it will be going to the force vector. Yeah. Okay. So basically, if you have in general, if you see k some component, yeah. So I will here write that it will have the various components. So this may, since we have taken one example, in example, this will have like this. Either you will have du over dx, dw over dx multiplied by some constant. Okay, so just write, let us say I'm writing b1 x. So this will be one form, right? Then k times u, this will be, right? K times u will be like this one, plus you have du over dx times w, let's say b2x dx, plus there could be in some scenario even so if you look at this, here even dw is coming into picture, right? And then so these kind of things are also there, yeah. So w, so and no, that I have pointed out already in this case. Then you have here you have w multiplied by this one, then you have w times u b3 x dx. So these are combinations are possible, right? So ku will be basically giving you this and this and this, yeah, this kind of thing. So what you see here from here, that since this is symmetric in du and dw, you will find a symmetric K matrix. Here it is when you have du over dx, here w, so it is not symmetric to v U and W are not symmetric. So in that case, this will give you non-symmetric. Yeah? It will give you non-symmetric stiffness matrix. This component will result, right? And here also, yeah, W and U are in the same, both are without any derivative. So this will also give you symmetric matrix. Yeah. Okay, so I mean, here you should not be confined to the simple examples that I take. Simple examples are important because that way we can derive in a class. Otherwise, if you take lengthy one, becomes very difficult. But if you solve the problems given in the book, then you will have different kinds of problems, and then you can find out this kind of scenario. In fact, you can see when you solve those problems. So please solve those problems, and that way it will be very clear. Yeah. So as you know that typically we have Kij in terms of depending on which form you have. So if you have this form, let us say, of this form, so in that case Kij will be 0 to L and dn1 over dx, dni dnj over dx, and b1x dx. See, it could be of this form. Yeah. Or if you have the second one like this one, then you will have dni dx nj b2x dx. Yeah. So second type. Yeah. Third type could be 0 to L, and then you have ni nj b3x dx. So this kind of you will get from here because you have w1 u, so you will have n and j like this. So this we have seen already, this kind of thing. So I'm just repeating. So this will give you the symmetric stiffness matrix. This also will give you symmetric stiffness matrix. This will give you non-symmetric one. And when you look at the non-symmetric one, from where it is coming, if you see in the example, it is coming from this one. So wherever single derivative is the part is in the equation, that is going to give you the non-symmetric one. Yeah. But typically in structural engineering, you will not get that. Yeah. In structures, you will not get that. In heat transfer, you are not going to get that. In heat transfer, you will get this. Yeah. So this is convective heat transfer. You will get it. Yeah. For structural, for diffusion, you can get this one because this is advection and diffusion problem. In that you get. Yeah. But remember that this when you have this also depends. This makes it more fluid dynamics comes into picture, and it becomes complicated. There could be some kind of instability which will be involved in also. You have to be careful. But anyway, but here we are learning the very basic course here. Yeah. And the first course of finite elements. So here we have to learn the basic techniques. Okay. It's not advanced course. Okay. Okay. So given this, the big picture that we are into, let's look at the problem we have been solving. Yeah. And the problem we have solved is you have the body force, this bx, and for this we have the so you have EA constants, and for that we have the exact solution we found out in the last lecture. And this is ux is equal to b naught over EA, and then Lx minus x square over 2. Yeah. So I think this is the solution we have, and we actually already we have done. Okay. So we had the 3 scenario. So the first scenario was was the exact solution. Yeah, so I think okay, so exact solution. Okay, so let me plot it. So far how it looks like. So you have x, you have ux, and the exact solution goes something like this. Yeah. Okay, so this is the exact solution. This is the number one. Okay, so number two is one two-noded element. Yeah, and what we got? We got like this. Yeah. Then we had the third one, two-noded element. Okay, and we got the solution like this, from here to here like this, and from here to here. So better than the number two, but still worse than number one, means exact solution. Now we want to delve into one three-noded element, and we want to solve it, and we want to see how the solution works out. Okay, so we can go ahead. Finally, we want a problem where we have like three-noded, like this one. We assume that this is x L over 2. So you can also write like this. You can say this is minus L over 2. This is 0, L over 2. Yeah. Then you can, here, you can have, actually this is the x system. So you have x here, and like this. What we are doing, we can just derive first. Yeah, we are going to derive the equation by given this system, because you know that whether this system starts here or here doesn't matter. So we have to take care of accordingly. And since B naught is constant, so B naught, that is the body force, is independent of this axis system anyway. We are not writing Bx as some value. This is B naught, Bx equal to B naught. Even if you change the axis, still B naught remains the B naught only. So we can actually do it. But in any case, you can, for finding out the stiffness matrix, you can change the axis system accordingly. You can find out. So if given this, yeah, so we can, instead of going into weak formulation and all, we can also directly do that's the message. And how we can do it, that's what we are doing. So we have u1 is in node number 1, node number 2, node number 3, and then u1, then you have u2, then you have u3. Yeah. Okay, and similarly there will be force also acting here. So you will have F1 applied here, F2 and F3. And accordingly, we can write U vector is equal to U1, U2, U3, transpose of that. Force vector F1, F2, F3, transpose of that. Now we only want to find out what is the stiffness matrix. Stiffness matrix, as you know, like K, in this case, we know already that how you calculate, we know, which will be, if you look at the weak formulation that we know now, K is given by, we write Kij is given by Ea dni dx dnj dx. So this also we know, right? The same thing we can apply here, right? Okay, now the only thing is like how to, or you can also write K is equal to 0 to L and Ea, and then we have B matrix, right? We wrote B transpose B, right? And then dx. Yeah. So we have the B matrix we called. Yeah. So this is whole K can be written like this one. Yeah. Or component of that we write like this one. Yeah. So this we have worked on already. So once you know the how the weak formulation will look like, immediately you can this is for a 1D problem, this is the standard that we can use. For what kind of problem? For 1D elasticity problem. For that it is valid. Yeah. Otherwise you have to look at the weak formulation. But weak formulation we have already looked at, and already we have found that for this problem, when we were working on 1D, the single two-noded element we looked at, before that we converted that into a weak formulation. From there we got this. So same thing will be applied here also. Now, how to formulate? Now we have, if you see, there will be Kij. Now there are three types. I mean, if you I equal to 1, 2, 3. Why? Because since U and F are 3, K also has to be. So this will be 3 by 1. This is also 3 by 1. So K has to be 3 by 3 matrix. Okay, so here I is 1, 2, 3, and this is how this one is. Okay. Now, how to find out N1? Here we will have 3 interpolation functions. So you write Ux equal to summation of Ni, right? Nix Ui, right? So here we are writing Ui, right? I equal to 1, 2, 3. This is for 3-noded. Because why 1, 2, 3? Because this is 3-noded, right? You have 3 U values for node 1 and 2 and 3, and for every one there has to be one interpolation function. Yeah, and this is how U is defined, and that really means if you look at automatically, since this is given like this one, that will be tells you that U at x equal to minus L over 2 will be equal to U1. U at 0 is equal to U2, and U, right, U at L over 2 equal to U3. Right? Okay. So we have this. Also, this we want because this is how it is defined, and this will only be possible when N1 at minus L over 2 is equal to 1, N1 at 0 is equal to 0, N1 at L over 2 is equal to 0. Yeah. So how is it possible? You are giving three conditions. It means N1 should have 3 coefficients. So that N1 has to be equal to C, let's call it alpha 0 plus alpha 1x plus alpha 2x square. It should be something like this. So that you have 3 conditions and you find out the value. So that means N from first one, N1 minus L over 2 is equal to alpha 0 plus minus alpha 1 L over 2 plus alpha 2 L square over 4 has to be equal to 1. Similarly, N1 0 is equal to alpha 0 is equal to, right? Is
0.
Equal to 0. Yes. Then you have N1 at L over 2 is equal to alpha naught plus alpha 1 L over 2 plus alpha 2 L square 4 is equal to 0. So you can actually write equation, right? And you can actually write like this. You can have, so how do you write the same equation? If you have to write, then we can have
minus L by 2, L square by 4.
Yeah, so you can write here 1 minus L over 2 L square 4 and so on. Yeah, so 1 minus L over 2 L square over 4, then then what? You will have here 1,
0.
0, 0, 1, L over 2, L square over 4. And here you will have alpha naught, alpha 1, alpha 2 is equal to 1, 0, 0. Yeah. So then you can find out, inverse it, alpha naught, alpha 1, alpha 2 is equal to, you can find out 1 minus L over 2, L square over 4, 1, 0, 0, 1 L over 2, L square over 4. Inverse of that, multiply by 1, 0, 0, you can find out these alpha naught, alpha 1, alpha 2.
Sir,
Yeah,
so
yeah.
when we know alpha naught is 0, why we are not directly putting?
You can put that.
Okay.
Yeah, yeah, sure. You can put that and then you can do that. Yes, possible. Yeah, you can do that. Okay, now any problem, guys? Everything all right? Here, I think I made a mistake. No, it's all right here. So here alpha naught, alpha 1, 0, 0. Yeah, it's all right. Yeah. So in any case, we have to. So you can also see whether everything all right or not. So you can actually find out the value of alpha naught, like all the values accordingly. Yeah. Okay. Now, similarly, you can find out, you can have n2x is equal to beta naught plus beta 1x plus beta 2x square. Similarly, yeah. And similarly, you can formulate and you can find out that in that case, 1 minus L over 2, L square over 4. Then you will have 1, 0, right? 0 and 0, 1, L over 2, L square over 4. And then you have beta naught, beta 1, beta 1 square is equal to 0, 1, 0. Yeah. And similarly, you can find out n3x equal to, let's say, gamma naught plus gamma 1x plus gamma gamma 2x square, right? So in this case also you can get 1 minus L over 2, L square over 4, 1, 0, 0, 1 L over 2, L square over 4, gamma naught, gamma 1, gamma 2 is equal to 0, 0, 1. So either you can use this to invert, or you can find out this one, or even better, what you can have some tricks, very fast calculation. How do you do that? This will work regardless of where the axis is. You just have the equation, you get the 3 equations, right? And you have the 3 coefficients. You can find out, you can construct the n1, n2, n3, and you can integrate. But there is another way of doing the same thing. Finally, what we want, see here, we have 1, 2, 3, and if you look at so this is x equal to minus L over 2, x equal to 0, and x equal to L over 2. Now we can have n1x. What do we want? We want it to be 0 here and 0 here, that we have seen. So that means n1x has a root here and here, right? And that means you can write n1x equal to some constant, let's call c1. Then we have x, because there's a root at x equal to 0. And then there's a root here as well, x equal to L over 4. So we write x minus L over x minus L over 2, right? Only thing is we don't know what is the value of c1, but we know that n1 minus L over 2 has to be equal to 1. So from here we can get some clue. So c1 multiplied minus L over 2 minus L over 2 minus L over 2, right? So what do we get? we get equal to C1, and then we have L square over 4. No, 2 only, right? So this becomes minus L over 2, minus L multiplied by minus L over 2, the L square over 2. So equal to C1 L square over 2. And that has to be equal to 1. That tells us that C1 equal to 2 over L square. And hence, we can find out that N1 x is equal to 2 over L square x minus L over 2. As simple as that. Yeah. Similarly, you can find out for middle one, and middle one is what? We want 1, 2, 3, n to x is equal to. Now it is x equal, this is L over minus L over 2, 0, L over 2. This one has to 1 here and 0 here and here. So minus L over 2 plus L over 2 has to be the root. So let's call it C2 multiplied by x plus L over 2 and x minus L over 2. x plus L over 2 because this has to be the root. This minus L over 2 because this passes through both of them, right? Meaning that it has 0 at both the places. So this is the thing. But we know that n to 0 has to equal to 1. So that means C2, and then we have L over 2 minus L over 2, right? Equal to C2 minus, that means equal to minus C2 L square over 4 has to be equal to 1. That tells us C2 equal to minus 4 over L square. Yeah, and hence we have n to x given by minus 4 over L square, then x plus L over 2 multiplied by x minus L over 2. Similarly, you can find out the third one. So third one, minus L over 2, 0, L over 2, and then we formulate n3x equal to, yeah, so it has root this and this also, so we'll have a C3 x plus L over 2 and then x, right? And n3 at L over 2 has to equal to 1, and that tells us C3 L over 2 plus L over 2 multiplied by L over 2 is equal to 1, and C3 is equal to 2 over L square, right? And hence n3x equal to 2 over L square x plus L over 2. Yeah. You can actually plot it. Here you have 3 noded minus L over 0, L over 2. Okay. From here to here is 1. Right. So like this is 1, goes like this one. Let us say, and plot number 1, n1, 1 here, 0 here, 0 here, and this is quadratic, means it will have only one bending basically, right? So it has to go here and go here. It cannot go like this, right? So you know this is quadratic. So it will have only one bend somewhere. Means it will change the slope somewhere, right? So it is it will go from here and it has to be 0 here, and since this also have to 0 at the last node, it has to go like this. So this one is n1. Yeah, so let's write n1. Number 2, n2. n2 has to be 1 here and 0 here and here. Only way possible is you go like this. Right? Okay, so this is n2. Okay, then we have N3. N3, you know that has to be 0 here and 1 here. And only thing possible is go from here to here and here. So you can also plot it. Actually, you will get exactly the same. Yeah. So whatever we got, you will get the same thing. So this is how the three shape functions will look like. Yeah. What you see also interesting that if you see n1 plus n2 plus n3, summation of ni, it will be 1 everywhere. Yeah. So here it just n1 is there. If you add them anywhere, this meaning n1 plus n2 plus n3 is equal to 1. Yeah. Okay. Okay. So here we found n values. Now next is finding out the stiffness matrix, and we can do very easily. So let us say we have to find out K11 is equal to 0 to L EA, yeah, and dn1 over dx square dx, right? So where dn1, so n1x is equal to, as you know, 2 over L square, then x minus L over 2. Yeah. So we have this equation, and hence dn 1 over dx will be equal to 2 over L square, then x minus. So you can also expand it, d over dx, x square minus L over 2x. So 2 over L square, 2x minus L over 2. Yeah. Okay. So this we can put it here. So k, let's go to the next. So K11 is equal to 0 to L EA, which are constant, and then dn1 over dx square of that. And what we got? We got 2x, right? 2x minus L over 2 square of that, and then we have to also make this a square, so 4 over L4. So 4 over L4 dx. Yeah. So will be equal to EA, which are constant, 4 EA over L4, right? And multiplied by, we have this, so we can write 2x minus L over 2 cube of that divided by 3 multiplied by 2, right? So this cube and 2 is multiplied to x, so we write here, and 3 because we have 3 here, right? So we have like this, L2 0 is equal to 4EA over L4, and put okay, so we can also have 1 over 6 here. We have take common here, so 1 over 6. Then put L here, so it becomes 2L minus L over 2. Yeah, so 2L minus L over 2 cube minus L over 2 cube, right, is equal to 2EA over 3L4 multiplied by, here what do you get? For 3L over 2, you get 3L over 2, so 9L cube, sorry, how much you get? 3, so 3, 27, right? So you get 27L cube over 8. You guys are with me?
Yes, sir.
Yes, yes, sir.
Okay. So 27L cube over 8, and then you have minus plus because this is odd number here, so it becomes plus, and then you have L cube over 8. Yeah. So 2EA over 3L4 multiplied by, you get 28 L cube over 8. Yeah. Okay. So how much we get now? So we have 8. We get 7, right? 8 times, sorry, we have 8 here and we have 56 here. So 7 becomes 7 over 3 EA, and then L cube here, L4 here. So EA over L multiplied by 7 over 3. Yeah, you guys are with me? So K11 is equal to 7 over 3 EA over L. Got it? Okay. Okay. Now K1, if you want to do it, then how will be 0 to L EA dn1 over dx, dn2 over dx. Yeah, is equal to 0 to L EA dn1, we know 2 over L square multiplied by 2x minus L over 2, right? That's what we got, 2x minus L over 2. Okay, multiplied by the second one, n2 over x, dn2 over x. Now n2 is equal to what? N2x. So n2 is here, minus 4 by L square, x square minus L square over 4, right? So minus 4 over L square. So minus 4 over L square multiplied by x square minus L square over 4. Yeah, so dn2 over dx minus 4 over L square multiplied by 2x. That's it. Yeah, so equal to minus 8x. Minus 8x over L square. Yeah. So K12, we are going to multiply this to this. So we are going to multiply minus 8x over L square dx. Yeah. Then you can simplify and you can find out K12. So K12, if you integrate that, you will get K12 will be minus 8 over 3. You can work out, so you can work out that. So minus 8 over 3 EA over L. Yeah. So you just have to integrate this one. Yeah. If you integrate, you will get this value, minus 8 over 3 EA over L. Okay. Then K13. K13 is equal to 0 to L EA dn1 over dx dn3 dx. Yeah. So n3 is equal to n3 is equal to, we have a 2 over L square, and then we have x plus x over L over 2. So dn3 over dx equal to 2 over L square, and then you have x square here, so you get 2x plus L over 2. Yeah, so you can have K13 is equal to 0 to L EA, then you have 2 over L square, square of that, and then you have you will have minus L over 2, right? So you will have 2x minus L over 2 and multiplied by 2x plus L over 2 dx. Yeah. Okay, if you work out, what you will get is K13 is equal to 1 over 3 EA over L. Also, you can see, like from the mechanics point of view, like what it says, like all the forces. So if you look at, let us say, we said that here you are giving unit U1 equal to 1, right? And whatever the force is needed, you are going to measure. So this will be K11, this will be K112, this will be K13. Yeah. So that really means K11 plus K12 plus K13 equal to 0, because they represent the same loading condition, right? So here it is fixed. What you are doing? You are fixing at the other two nodes, and you are giving unit displacement here, and you measure the forces. So F1 is equal to this, F2 is equal to this, and F3 is equal to this. So since all the forces here are K11 force, K12 force, K13 force, all the has to be at 0, if you remember the chapter number 2. So you can also just determine K11 and K12, and you know that K13 has to be so K13 was minus of K11 plus K12, right? And basically, and you can find out that way this will be 1 over 3 EA over L. Yeah. Any question, guys? Any questions so far?
No, sir.
Yeah, okay. Okay, so similarly for other terms, you can find out that way. And next will be K. Okay, so far what do we know? We know K is equal to, and we have EA over 3L, EA over 3L. And so far what we get? We get 7 minus 8 and 1. And it's going to be symmetric, because you know that dn1 over dx multiplied by dn2 over dx, when ni and nj both are symmetric. So it is, you are going to get symmetric only. So 7 minus 8 1, 7 minus 8 1. Yeah. Others we don't know what that is. If you know this one, you can guess what it will be, because if you add them together, it will be 0, and you can find out what the value will be here. And whatever the value you are getting here, you can have here. Other trick also, remember that whatever you get here and here, you see, you have EA. These values is symmetric, like this element is symmetric. Means symmetric in the sense that 1 and 3 can be replaced. So if you require K11 to displace this by U1 while keeping these two constant, keeping these two fixed, if you fix this one and fix this one, and if you apply a displacement U1, you will need the same force as K11, right? Either you compress it or extend it. It's the same. You need the same force. Yeah, that means you can also guess basically K11 is equal to K33, because 1 and 3 are symmetric. Whatever force you need here to displace this by 1, you need the same force to displace this by 1. right? While keeping other two fixed. So in fact, based on this mechanics, actually also you can extend it here. Yeah, so that will save you time. Yeah, so in exam scenario, this is going to save you time if you know this. Otherwise, you can calculate the way we have done earlier. Yeah, so since we know that this 7 has to appear here, we can also write 7 here. If you write 7 here, total has to be 0, so it will be minus 8 here. If it is minus 8 here, you also get minus 8 here as well, symmetric, because minus 8. This is minus 8, this is minus 8. Total has to be 0, so you get 16 here. And you have the stiffness metric constructed. Yeah. Okay, once you have that, now the problem, right? So looking at this, coming to the original problem, you are going to fix it, and you have D naught here, and then you are going to solve it. But force we don't know yet. And what is the force? F equal to F1, F2, F3 transpose of that, and Fi is given by nothing but B naught in this case. Yeah, in fact you can make it Bx Ni dx 0 to L. Yeah, and in this case is constant, so B naught will be there. Yeah, and then Ni is 2 over L square x minus L over 2, right, dx. So equal to B naught 2 B naught over L square, and then you have x square term here, right? So x square, so you get x cube over 3 minus L over 2, and then you have x square over 2, right? 0 to L, so L to 0, and will be equal to 2 B naught over L square, and then you have L cube over 3 minus L cube over 4, that's it, is equal to 2 B naught over L square, yeah, multiplied by L cube multiplied by 1 over 12. So what we get? You get 2 here and 12 here, right? So 2, 12, 1 over 6. L square here, L cube here. So L, B naught L over 6. What we get? F1 equal to B naught L over 6. Yeah? Okay. So we got that. Now, what will you do the next thing? Oh, okay, guys, we made a mistake. What? Did you catch the mistake? Did you catch the mistake, guys? No?
Sir, I think the limits.
It has to go from minus L over 2 to L over 2. Yeah? Okay, but somehow we got the same answer. Yeah, but please do this, okay? So now I realize we made a mistake here. So accordingly, please change it,
So might be the function is such that the limit from minus L by 2 to L by 2 is same as 0 to L. Like.
Yeah. So, but we made a mistake, and when we are doing for the B, then we realized that there's something wrong. So similarly, minus L over 2, so you have to do like this one. Yeah, so please do all these corrections. Okay. Okay. So so far so good, but here we have minus L over 2, L over 2 minus. Okay. So this thing is wrong, so we will not write this. So let's go to the, I think this is wrong. So, okay. So what we get here is 2b naught. So f1 is equal to 2b naught over L square 2b naught over L square, and then we have L over 2, so L cube over 24. Okay. And then L over 2, and then we have L over 2 here, so L square over 4, L cube over 16, right? So here we have L square, so L cube, and 2 here, and 4 coming from here, 16. So L cube minus 16, okay, and then we have minus, this term is will add, right, but this will be is going to cancel the previous one. Yeah, so this is minus, so this is going to plus equal to the same, the first value, so we'll have plus of L cube 24, and then we'll have you will have plus of L cube over 16, so that it cancels out. Okay, so is equal to 2b naught over L square, then we have 2L cube over 24. Yeah, so we have b naught L over 6 only. Yeah, so here also we get the same value, looks like. Yeah, so you get this. Okay, please see if we made some mistake, so you have to check. Okay, so but I'm assuming we are getting b naught L over 6. So if again it is symmetric for f1 node 1 and node 2, right? So it will you can find out, use the equation f2 f3 is equal to minus L over 2 to L over 2, and you will have n3x b naught dx. But you note that this is symmetric, f1 and f3 will be symmetric. I mean, both will have same value, so b naught L over 6. Okay, even you can find out f2. So f2 is equal to, you can find out 0 to L b naught n2x dx. What is the value? Either you can put n2 here and you can integrate.
Limits.
Limit again. So we are used to 0 to L, no? Okay, so what is the value? Remember, whatever force we have here, see, this is B naught, right? And this is L total. Total force will be what? Total force is equal to B naught times L. And what you are doing, you are using this interpolation function to redistribute it. Means from this continuous force, you want to make it discrete force. You want to same thing is going to be redistributed to these two nodes, and you have B naught L over 6 here, B naught L over 6 here, but the total is B naught L. What should come here? Tell me.
So 2b naught by 3, 2b naught L by 3.
2b naught L over 3. You will get the same value here. You will get the same value. So total force is being from the continuous system, it is going to be a discrete system, and this is how it will be distributed. So F3 will be equal to this. So F vector is given to be B naught L over 6, and then you have 1, you have 2, maybe 4 here, and then 1 transpose of that. Yeah. Okay. So, and then you solve it. Given that, you can solve it. And so just hold on. I'll take just 5 minutes more. Sorry about that, but I think we have to finish it. Otherwise, you have to restart. So let me save it first. Otherwise, sometimes we lose it. Why I'm doing? Because it allows only 20 pages, so that's why I have to open a new page. Yeah. Okay, so yeah. So we know this one. Now next thing, we are just going to solve it. Okay, so just give me. Okay, so now we can solve the problem, and the problem is like this one, right? So you have B naught here. That's it, nothing else. So our KU equal to F. So you know that U1 equal to 0, and U2 we have to find out, U3 we have to find out, and we know that F3 is 0, right? There is no force applied here. So what is the equation? We have EA over L, 3L, and then you have 7 minus 8, 1, then you have minus 8, 16 minus 8, and then you have 1 minus 8, 7, multiplied by 0, U2, U3 is equal to F1. F1 we got the F1. So F1 value is B naught L over 6. Yeah, but remember that this is the force that we get from this, but there are additional force here we don't know, right? So there will be reaction force here, unknown force here, right? Reaction force will be there, so we have to account for that. So we'll write plus R1. Let's write it like that. Okay, because why? This is a fixed, and since U is 0, the force you cannot prescribe. You cannot say this is the force. Got it? So we have to write R1 because this is unknown. So we write like this. Then number 2 is not constrained, so actual force will be the one we get. So 2 B naught L over 3, and number 3 is B naught L over 6. And now we are going to solve, right? So you can find out from this one, we invert it. So the equation becomes U2, U3 is equal to then 3L over EA. Okay, and then we are going to invert this one, right? We write this multiplied by this. So we have 7, 16, 8, 8. 7, 16, 8, 8. Okay, then we have to divide it by
1 by 48.
1 by 48. Okay, so multiplied by, let's see, let's write 48 here. Okay, so Okay, so we got the 48, and then we have this value, right? So 2 B naught L, we can write here B naught L over 6, sorry, 2 B naught L over 3, right? And then B naught L over 6. So B naught L over 6. Yeah. And then you can find out the value of U2. Yeah. So what do we get? U2 and U3 value is equal to 3L multiplied by B naught L. B naught L over 3 we can bring here. So at least B naught, let's write B naught L, which will be common, 48 EA. So B naught L, we put it here. Then we will have
20 by 6.
20 by 6.
I guess around this only. 20 by 6.
Okay.
10 by 3.
Okay. So 10 by 3, I'm just writing 10 by 3. And what is the next one?
32 by 6 minus 16 by 6. 16
Wow.
by 6. 8 by 3.
8 by 3. Okay. Okay. So what do we get? So which is equal to?
So B naught L by 24 EA, I guess. And inside 5 and 4.
So here we have B naught L square, right? So I think, so B naught. Okay, yeah, you have to check that. Okay, so let's write it here. First one will be 10 over 48, so it becomes 5 over 12, right? 24. 5 over 24. First one becomes what?
4 upon 20 and 5 and 4 upon 24, second one.
Yeah. So 5 upon 24, B naught L square over EA. And second one will be 1 over 6, right?
Yes.
So B naught L square over 6 EA. Transpose. Oh, what was there's something wrong in here. You know, so you should get U3, which will be equal to the actual solution. An actual solution will be, if you look at it, it will be L square L square minus L square over 8. So okay, so our Ux is equal to B naught over EA, and you have Lx minus x square over 2. So so our system is what? Our x starts here, right? So actually you put UL is equal to B naught EA multiplied by L square minus L square over 2, right? So it becomes B naught L square over 2 EA. It should be like this. Yeah. So there is something wrong here in the equation.
Sir, it will not be 8 by 3, it will be 8 only, I think.
Where?
Sir, where you have written 8 by 3 in the math. 8 1 8 16 plus
Here.
by, yes sir.
Okay, it will be just 8, you are saying. Okay, you do the just see. Okay, so finally U3 you should get U3 you should get is equal to this expected values, the expected, yeah, and U2 accordingly, because you will get the exact solution in this case, yeah. So U2 value you should get B0 over EA and L square over 2 minus L square over 8. So B0 over EA, and then we have for 3 L square over 8. Yeah. So U2 3 by 8. So how much we are getting? So there's something wrong. Yeah. So we should be getting the exact one. Okay. So we have to see where we made mistake. Please go through it. Please let me know where we made mistake, but we should get the exact solution. Yeah. This is because we are we know the solution is quadratic, and our test function is quadratic. So we should get the exact solution, right? So hence the values. Okay, guys. Is okay? Yes, no, what?
Yes, sir.
Yes, sir.
Sir, I have a doubt, other
Yeah.
doubt.
Mm-hmm.
Sir, okay. Sir, like we have been given ux and an equation. Like ux is a trial solution is of the form a plus bx plus cx squared, and we are given two essential conditions, or u0 equals 0 and u1 equals 0. Like, can we put these initial essential boundary conditions in this ux both? Because I'm like getting different answers.
Okay. So you are saying that there's some equation where there are two essential boundary conditions are given. That you are saying, right?
Yes, sir. So we are given a differential equation, d by dx in bracket x du by dx, and bahar we have minus x equals 0, this form. And we are given a trial function ux, and we will take wx also of the similar form. And then we are given two essential conditions. So when I'm putting it initially in ux, then I'm getting this b into x something x minus x square. But if I'm not putting, then I'm getting a different answer. And the Galericon, without putting the Galericon and Ritz method, are giving the same answer. And after putting, it's giving a different answer. So is it like some conceptual mistake that I'm making?
First of all, if any equation you are given and you have a u, let us say at one end, let us say we are talking about 0 to L, let's say, okay. So u at 0 is some value given, let's say u0, and u at L is also given. That's what I'm saying, right? So it's
Yes,
given
sir.
like that. So remember that your function has to solve, meaning that your function has to have both of them, right? I mean, this boundary condition has to be like satisfied, right?
Yes, sir. And
Yeah.
what if we end up getting different values of b two times and still satisfying the boundary conditions? So that is the problem.
Yeah, so depending on your expression, you can have different kind of solution. So you can have x, let us say x equal to, you can
A
have
plus bx plus cx square.
yeah, okay. So you can have, since this had to be like this one, so you can have, for example, solution will be that let us say we call it a plus bx plus cx square, right? and then u at 0 will be equal to a only, which is equal to u naught. So say it will be u naught plus bx plus cx square types, and then u at L is equal to u1, so it will be equal to u naught plus bl plus cl square, right? So from here we get a value of b, let us say, right? So finally you end up with ux, which is a function of, we will have some c, and it will already will have all the values. So there will be only one
Variable
value,
or coefficient.
yeah. So which will be which this will have. Now you tell me what happens.
Now here is the problem. If I don't put like A, I'm getting always 0. That's fine. But with B and C, the problem is that if I'm not putting the second boundary condition, if I'm not making it satisfy, then putting it in the equation is giving a different B, and not putting the essential boundary condition is giving a different B. And like some of us have solved this, so this is the issue.
You are saying in one case you are putting the value the way I have done here, and then you
Yes,
get a
sir.
different value.
Yes, sir.
You won't put this value here, and this if you find out the value of B and C, then you get
Yes, sir.
different value. That's what you are saying.
Yes, sir.
Yeah, but in that case, boundary conditions are different, no? So I mean, when you say, when you're applying the Rikin method, your trial function has to satisfy the essential boundary condition to begin with. Otherwise, you will get something else.
Okay, so the correct method will be where we satisfy both conditions
Yes,
first. Okay,
yes,
okay.
you have to.
So, but what if later on also it is satisfying? Like, matlab, it is satisfying later on also, but it is different. So, is it? So, it's like wrong.
It's wrong.
Okay, okay, sir.
Yeah. So essential boundary condition has it has to satisfy to begin with. Yeah. So this is how you write the weak formulation. There itself you write. Yeah.
Okay, sir.
Any other question, guys? Okay, so guys, please check it. Okay, I think where. So let me see quickly. Okay, I think these are the calculations. So maybe I will recheck it. Okay, and then we'll discuss in the next class, means tomorrow. Okay. In the meantime, please you also see. Yeah, where the problem is.
Sir,
I
I've
think.
got the mistake. Sir, it's
Yeah.
not 48.
Okay.
I did it 112. It's 102 minus 64.
Okay. So how much is this now?
102 minus 64 is 38, not 48.
Okay.
But
Okay.
still,
So
it's going bad.
no, sir. There will be somewhere you will find that it will be like that. Okay. So please do it. Yeah. Somebody raised hand.
Sir, by mistake, sorry.
Yeah, okay. No. So please see where we have this mistake, and then we can find out. Okay, but we should go get the exact solution. That's the message. Yeah. So that's we should do. Okay, guys. Thank you very much for staying with me late. Okay. So I will see you tomorrow at 10 o'clock. Thank you.
Thank you, sir.
Thank you, sir.